inertia.
When they both have the same. Wouldn't they both have the same?
They would not. Again, red one, mass here, most of the mass here.
Oh, you
Blue
can't see
one,
through
most
that
of the
one?
mass here. Pardon?
Oh, you can't see through the red one?
Not there. You can see through these spots.
So, wouldn't it be the red one?
They have the greater moment of inertia. Why?
I don't know.
It feels right.
Yeah. I like red.
The answer on the test. Would it be the blue one because it's more mass that has to accelerate whenever you're turning it at the center point?
Okay, that's a valid way of looking at it.
It has more momentum because it's so far out on the radius, it's moving faster than the stuff on the inside. Or
Okay,
as
yeah,
opposed to the red.
that works. Another way of looking at it again, it's mass times the radius, the distance squared from the axis to where the mass is. So as R gets bigger, the moment of inertia gets bigger. So what would be the effect then? The blue one definitely does have a greater moment of inertia. How would you be able to tell? Just experimentally? Yeah, Corey's got it. If I move the blue one, sort of to get a sense of trying to do it as fast as I can. The red one, it's much easier to rotate this. This has a greater moment of inertia, a greater rotational inertia, which means once it's harder to get moving, and once it's moving, it's harder to stop it. That and okay, that does well enough. All right, so I'll start spinning.
Need someone to give you a push.
No. No. Occasionally suffer from vertigo. So if this kicks it in, I will excuse myself and then be back and hopefully not throw up or stumble into something. All right, so I'm going to start out spinning around and then I'm going to move the masses out. So what happens as I move the masses out?
Your arms are gonna get tired.
Besides that,
The moment of inertia becomes bigger.
okay? And what's going to happen to my spinning?
You won't go as fast. Or maybe the other way.
Sorry, didn't say it again?
You won't go as fast if you put your arms out. Air resistance.
It's not an air resistance thing.
Okay, never mind.
You're already spinning when you move your arms out, right?
Yeah.
So wouldn't it take you longer to slow down?
Taking longer to slow down. So you say that go faster?
Spin
Not
slower
necessarily,
as
your
it goes.
acceleration would be slower because the inertia is bigger, so you want to keep spinning.
Okay. So does that mean I'm going to speed up or slow down or no change?
I think you're still gonna slow down, but it'll be at a slower rate.
I think you're gonna slow down, but the force it takes you to stop is gonna be spread out over a longer span of time is what he's trying to say.
Ah, okay. Just give it a moment. Ooh. All right. Where have most of you, I guess I'm presuming here, but where is this most commonly seen?
Ice skaters.
Yes.
That was only a test question.
So as I'm spinning around, this mass right here, when I bring it in, is just basically coming straight this way. This mass right here, as I'm spinning around, I have to sling my arm around. So what's happening as I'm spinning this way, I'm slinging this arm around, I'm basically pushing myself in the direction I'm spinning, and then reverse going to the other direction. Put it in some sort of force.
You have a pressure point to stop motion sickness right here.
Say it again?
You have a pressure point to stop motion sickness, vertigo right here.
Oh,
3 fingers down from your wrist, right there.
I hope it works.
Works for me.
Any of you know the Epley maneuver? I know we only got a week and a half left, but, okay. All right, so I have some moment of inertia, I'm spinning around, so what I have is this moment of inertia, and I have some angular speed. Actually, angular velocity. As one goes up, the other one goes down. In other words, we have this idea that I omega initial is going to be equal I times omega final. I know there's sort of a leap there. If we did the analog, if we transliterate it into linear motion, what is the analog of moment of inertia? And angular velocity?
Velocities.
And what is mass times velocity?
Force. Like, momentum.
Yeah. So I times omega, this is angular momentum. And it is the third quantity that is conserved. Just like regular momentum, angular momentum is conserved in a closed system. There's rotational impulse. We call it impulse is equal to either force times time or change in momentum, whichever one's easier. If we're dealing with rotational, well, what's the analog of force?
Force.
The rotational analog,
Angular force?
there's another word for it,
Torque.
torque. Or, see who remembers? Since yesterday?
T2 Kumbaluka or something like that.
Not too bad. G2 Kombucha.
That was pretty close.
G2 Kombucha?
Yeah.
That sounds like a
There's
drink.
like one syllable.
There's no way that's a real word. There's no way. That's a real word? Like,
A person rather.
Is Jaquan a real word?
yeah, it's my name. Well, no,
Then
it's-
G2
it's-
Kombucha is a real word.
my fault.
Well, actually, it's two. It's a first and last name.
That's the first and last name?
Yep, G2, and then Kombucha.
G2 torque.
R2D2. Got it.
Let's put some of these pieces together. We got a lot of random ideas here, so let's sort of combine them into an all-encompassing problem. It's something with there it is. I can't write with my finger, but I noticed that my finger didn't quite blister, but it was getting to the point of almost blistering. I used only my finger. Yeah, I'm a weenie, so that's why I'm going with this. All right, I have a disc here. I have a disc here. It's being held up by something. I have a rod stuck to the end of the disc. Stuck to edge of disc, probably better. Let's give some specs here. We'll call this disc L and disc S for large and small. The mass, let's make it 5 kilograms. The radius, 0.4 meters. Small disc, radius, 0.1 meters. And the mass of the small will make 0.5 kilograms. Actually, let's make it 6. This will give it a mass of 3 kilograms, a length of 0.3 meters, and we have a hanging mass here. Remember that I don't think I've used a 7 yet. We'll make that a 7 kilogram mass. So the question is, what's the acceleration of the 7 kilogram mass? Now we gotta do a bunch of steps before we get there, but that ultimately, or I could make the problem, oh, even better than that. 2 questions. What's the acceleration of the 7 kilogram mass? And how fast is the rod going when it is pointed downwards? So, step 1, let's figure out the moment of inertia of the disc. Of the, we'll call it 2dr for 2 discs and a rod. Well, remember that ultimately, moment of inertia is an infinite sum. It's a sum adding up a bunch of things. So if I've got 3 different objects here, the moment of inertia is going to be the moment of inertia of big disc plus the small disc plus the rod. So let's take it step by step. So that will be I of the large disc plus I of the small disc plus I of the rod. So what's the formula for the disc? Moment of inertia of a disc.
1/2 mr squared.
Yep. So 1/2 mass of large, radius of large squared, plus 1/2 mass of small, radius of small squared, plus, and then the rod?
1/3, 112 ml squared.
Why'd you say 1/3?
Is the point not at the disc, which is at the
It's
edge?
not. 1/12 ml squared assumes what?
It's at the center.
But it's rotating around the center. Around the center.
Yeah. But this is rotating about this point right here. The disc, there's a gap here from the center to where that is. So for the rod, you've got 1/12 ml squared. This is a lot like my R's. 1/12 ml squared plus m, and this is mass of rod, times that distance squared. So that's 1/2 the length of the rod plus the radius of the large squared. It's now plug and chug. 1/2 times, what I did, that's times 5 times 0.4 squared plus small 1/2 times 0.6 times 0.1 squared plus, so this would be for the rod, the 1/12 times 3.
You're forgetting the 1 and 12.
Oh. Okay, probably not the last time I do that. 0.3 squared plus 3 times the distance that we're moving the axis from the center of the rod to the center of the disc there. So 1/2 times the length of the rod, which is 0.3, plus the large radius, 0.4 squared.
Point four.
0.4?
Yes. Point three.
Oh. 0.25? That's what too many zeros there? No, not 2.5, it's 2.25. Again, do I have one too many zeros there? Or am I completely off?
One too many zeros.
Thus, this. Point 7 8.
0.07. Oh wait, are you asking with the 3 or without the 3?
With the 3.
0.072.
0.072. All right. So the moment of inertia of the rod in this situation is just the sum of these two. So 0.07425. So I did that math right. And so the total moment of inertia is just the sum of the bits. So 0.47725 units.
Kilogram per square.
All right, so we now have the moment of inertia of that disk. Questions to hear? All right, let's see if we can figure out the acceleration of that 7 kilogram mass. As we've done so many times. Force diagram, yes?
That's the amount of inertia for the, like, every object or for the entire system?
For the 2 disks and the rod.
So, like, would it be true to say that the moment of inertia for the rod is that, or is it for all three of them combined?
This is just the rod.
Okay.
That's the small disk, that's the large disk.
Okay.
And so that would be all 3 combined. Since they're all going to be rotating with the same angular velocity, it's convenient to combine them like that. That answer your question?
Yeah.
Okay. Other questions?
How did you do the rod again?
The rod, I know what the formula is about the center of mass. But this is not rotating about its center of mass here. It's rotating about this point. So I have to use the parallel axis theorem. I'm basically moving the rod, my axis of rotation from this point to this point. So that would be h in the parallel axis theorem. So it's the moment of inertia about the center of mass plus the adjustment factor for moving the axis of rotation. Is that sufficient?
Yeah, I see.
By the way, when I did this on a test, the first question was, what's the moment of inertia of the big disk? What's the moment of inertia of the small disk? What's the moment of inertia of the rod? What's the total moment of inertia? If you look at the old test, this is the part of the Rube Goldberg test, which in terms of for studying is actually very useful. Just because it covers just a whole lot of everything we've done. All right, force diagram. What are the forces acting on the mast right there?
Tension line.
Down.
Okay. And what are the forces acting on my,
Donut.
yes, donut? With a knife at its side. Or it's round enough, could be my cousin Robert.
Poor Robert.
No, had no sympathy for that asshole. I probably shouldn't have done that on video, but you know,
It's okay. I approve.
We can edit that part out later.
nah, he knows what I think of him.
Is it tension down on the small disc?
So tension down here, yep.
Weight of all of them?
We'll make some concession, yeah, we'll have the weight of all of them. This technically has its weight acting here, but I'm just gonna overlook that. That is not the weight you care about. So we just have this total weight acting down, weight of donut.
Is there friction?
No, it's not complicated. Did you want me to throw friction into it?
No.
All right, Ryan has spoke first, or indicated first.
Is there like normal forces in all three of the things, or we not?
There's something holding this up. I didn't really address that. There's something holding it up. So there would have to be a normal force here. But ultimately, it's not gonna matter.
So there's not like a normal force between the rod and the bigger disc?
Say it again?
There's no normal force between the rod and the bigger disc?
It would, since I'm considering this one object here, in terms of rotating, I don't have to, that would be an internal force. Anything, any force here would be internal, and we ignore those. All right, this is basically it. Equations of motion, or actually